Okay, so our second Simpson's rule video, and this one's about real life applications, and it follows on from the first one where we said we use Simpson's rule as a numerical form of integration, or a form of numerical integration, and we do this when usually the antiderivative is unavailable, so we don't have any means of finding the antiderivative. There might not be a calculus method available to us, or we might not know it. And the other method is basically when we have data and it doesn't appear to form any sort of discernible function. Alright, so function, well, it might not be available again. So they're the two main things. We dealt with the first one with our previous video, sine root x. Okay, and perhaps you've practiced some other ones. Another example actually would be, while I'm talking about this first one, something like this. So this one's a fairly famous one if it's from 0 to infinity, but even if we go something like this here, sine x over x. Alright, so there's no antiderivative available to us based on the methods we know. So anyway, getting back to data, let's look at an example. I alluded to this in the previous video briefly, and we've got the width of a cutting is 80 meters and has a depth of 50 meters. A measurement of height h of the cutting is taken every 10 meters. So this might be for a road cutting. So this might have been a hill, and they've cut straight through and created a profile like this, and at each measurement a measurement h is taken. Alright, and this one is 80 meters long. They're taking cuttings, measurements of the height of the cutting, alright, every 10 meters, so they'll go along like that up to 80. And the main assumption here, it's very simplistic, I suppose, but it has a constant depth of 50 meters. So that is probably not realistic, because usually the hill will not be consistent, but into the page it's a consistent shape. So that cross section, even though the height varies, the cross section shape is consistent. Okay, so we're going to treat it like a prism. So to speed things up, here's the surveyor's data. Okay, and this is what separates this from our previous video. However, we're still going to use Simpson's rule. So the area approximately equals W on 3 outside of x plus 2e plus 4o. And I'm using a notation where x is the extremes, so the end values, e is the even values, and O, that's not a 0, that is an O, is the odd ordinate values. Now, by the way, we're finding the volume of this, so we're going to find the area and then multiply it by the depth of 50. So we need W first, W the strip width. Well, it's pretty obvious from the given data that it's 10. Okay, so they've taken 9 measurements, and that creates a strip width of 10. So it's good that that's constant, and we note that down. We need to look at the extremes, the sum of the extremes. Now we don't need to substitute into the formula because there's no function, right? So the extremes are 0 and 0. Well, that's 0. And the evens, I might go 2e to save a later calculation. Now be careful here, we need to relate it back to what we know. In this relates to the A naught, so it's measurement 1 but A naught. Okay, so just be cautious about that part of it. So I'm going to go to the extent of writing all of those in. Now we can see which ones are the evens. So even because it's 2, even because it's sub 4, even because it's sub 6, and A8 is already taken up as an extreme, as an endpoint. We have 4.5, 5, and 3. And that comes to 25. Okay, let's do 4 times the odds. Okay, so the odds are 2, 6, 4, and 2.5. And we get 58 for 4 times the odd. Now we're ready to sub that into our formula for Simpson's rule. So we've got 10 on 3 outside of 0, which I won't write, 25 plus 58. So we get 276.6 recurring, so depends on how many decimal places we go. For the volume, we have the following there, multiply it by that 50, and the volume of land or rock or whatever it is that needs to be removed is 13,833.3 recurring cubic meters as an approximation. Of course, if the surveys did more strips, you could have a perhaps more precise answer there. That's probably sufficient, I would guess, for that scenario. By the way, technology has a great role with Simpson's rule. And for example, a spreadsheet could have, for this sort of thing, especially if there's a lot more measurements, a spreadsheet would be quite useful. And also, even if it's a function too, like the one I'm about to show you is for the function y equals square root of x. That could be Simpson's rule could find the area under the curve for that via, say, Microsoft Excel. An example might look like this spreadsheet here. So you can see that we've got values there for an area, and we can change parameters, and you can see we've got A, B, N, and W all set up there in column G, and some of those parameters are changeable, and you can, that especially on a large calculation, that would be good using Excel.